right, number 3 on the required review. 2 letters are selected at random from the word ideas. What's the probability of selecting 2 vowels? Okay, so let's see here. So when I go to get my first one, let's say I took the word ideas and I cut it up and I put it in a hat. How many vowels do I have a capability of pulling out? Okay, I have 3. How many total letters are there? 5. Okay. So then let's say, okay, I drew in and I pulled out the I. Okay, that's still in my hand. How many vowels are left? 2. How many cards are left in the hat? 4. So then, since it's probability, you multiply your options together. 3 times 2 would be 6 over 5 times 4 is 20. And reduce it down. And you absolutely could. Yeah, on a lot of these, yep. And on a lot of these, you could absolutely go with permutation combination type language and use the formulas with that too. I just tend to move this way when I can. Just okay. So 6. Ben's watching a comedy, a horror film, and a foreign film this weekend. How many ways can he order his movie marathon? All right. We got 3 movies. Uh-huh. Because, yeah, he can watch any of them with the first, but once he's watched the comedy, he's not going to watch the comedy again. So he's got 2 options left, and when he finally gets to the end, he only has 1. It depends on what you're trying to do. Like, for instance, if there'd have been a part here at the end that said he can watch the same movie twice, then it could be 3 times 3 times 3, because he might watch the comedy 3 times in a row because he's just laughing so hard he doesn't know what to do. Or you may have a license plate where it says, you know, you can repeat digits. That's when it just stays the same number. If it says without repeating, or it's something where it kind of makes sense that if you do it the first time, you wouldn't do the same one again. Number 1 is you are supposed to design your own experiment. Yes, sir. 14. All right, let's flip over. All right, if a couple is planning on having 3 children, what is the probability that all 3 are girls? Okay, now again, I have options here, but this is, again, the way I would kind of look at it. So I'm like, okay, we're going to have 3 kids here. So when I go to have my first child, what are the possibilities? Boy or girl, okay? So what's my chances of getting a girl that first time? Half. 1 out of 2. I'm getting a boy or I'm getting a girl. Now, as I move along, is it going to matter when we're pregnant with the second child what we had the first time? No. So what's my chances still going to be of having a girl? And then it'll be the same the third time. Now, if the idea of multiplying these out kind of confuses you, there is a way to do this visually. I could, if I wanted to, say, okay, well, I'm having kids here, so, all right, so the first time I have a boy or a girl. Well, then from there, each time I can have a boy or a girl. Okay, from there each time I can have a boy or a girl. And I'm sorry for getting squished here a little. But here's what I would find out at the end. I'd say, okay, my last branch tells me how many options there are. 1, 2, 3, 4, 5, 6, 7, 8. And the only one that goes all the way through, G, 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 is this one on the very bottom. So 1 out of 8 possibilities. So if you're more visual, you'll have enough time on this test. Draw out a tree chart, sort of like that in number 16 would be, and let that help you answer the question. That may go along with what we discussed earlier, but I will hit that up in just a second. Yes, sir. Okay, let's hit up 16 and 17 here, because this kind of goes along with our tree diagram idea. So, all right, the math team has 8 juniors and 13 seniors. Okay, I'm just going to write that in here. there are 5 junior females. So when this breaks off here at the end, I have female and male, and the same with the seniors. I have some females and some males. Now, what do I know? I know there are 5 junior females, and I know there are 6 senior females. Now, through process of elimination, how many male juniors are there? 3, because there's 8 juniors and 5 are females, so 3 are males. And what about senior males? 7. So now we have to watch very carefully on wording. When the magic word or comes up, that typically means we're going to be adding probabilities together. So first I'd look and I'd say, okay, the probability of finding a senior, I know there are 21 total students, so my probability of finding a senior would be 13 out of 21, because again, we're just looking at it in general. It would include males and females. Or finding a female. Well, I've got 5 females that are juniors and 6 females that are seniors. So that'd be 11 out of 21. But then I want to make sure I don't count anybody twice. So how many senior females are there? 6. So I have to take those back out. So 24 minus 6 is 18 over 21, or 6/7. That's different than saying senior given female, like we were doing before, because then we'd look for females and then see which ones are seniors. With the magic word or, we do each part and then subtract the overlap. So my chances of getting a senior or a female are pretty good. Let's say, though, I'm going to go past C for right now and go down to D, because this might confuse somebody if they were kind of thinking, no, that can't be right. Yeah, it can be. What's my probability of finding a junior or a senior? There's 8 juniors out of 21. And there's 13 seniors out of 21. And there's no such thing as being a junior and senior at the same time. Well, wait a minute, that's 1. Right. You have a 100% chance, 100% probability of it being a junior or senior, because that covers everybody. So if you get an answer that goes all the way up to a whole, a 1, that's okay. If you get an answer that's over 1, that's not okay, because yep. Because B and C are very similar in their way. It's just now you're talking juniors and males, but the setup for B and C would work exactly the same way. And then the one thing with Venn diagrams I want to make sure that we're being careful of, because the one on the test is going to be similar to this again. It's not going to be 3, it's only going to be 2. But here's what you have to watch out for. So, okay, as it turns out, 36 students say they would like to take band, and 52 say they would like to take choir. Only 14 say they would like to take both band and choir. Okay. So we've got band, we've got choir. We always want to work inside out on these. So 14 would like to take both. Okay. So then, I'm like, all right, I got my band circle, and I got my choir circle. All right. So thank you. If 36 students total want to take band, I've already taken up 14 of them right here. So how many band students do I have left that just want band? 22. Okay. Choir, I have 52 students who want to take choir, but 14 are already spoken for. How many are left? 38. So 38 only want to take choir. How many students total are taking one or the other? Now, here's the part that gets interesting. Because you look at that and you go, well, do I count the ones that overlap? Sure you do in this case. Because I'm not looking for how many take band or choir. I want how many take band or choir or both. So for the total number,
Can you subtract it?
nope, no subtracting on this one. It's different, and I'm glad we can still see the top. If I were asking for band or choir, we'd only want those, okay? But we want the total number of students. So whether you're taking just band, just choir, or both, I have to count you.
So that's any choir when it says total?
So when it says total, right, I want to know band, choir, and both. I want to know everybody. So how many total would it be if I add all these up? 74. And we found boo-boo number 1 of Hardee's. So I look over there and it says total 88. Now, how would I get a total of 88? What could have happened?
I did that too.
Well, and you know, and I can see how you can. Now, how do you get 88 originally?
You add
36.
Right, you just look at 36 and 52 and you'd say, okay, you know, there's 88. This is the situation where if you're trying to find total, that you would have to subtract the ones that are in common. Because the 36, as we see here now, includes the 14 that take both. The 52 that just take choir includes the 14 that take both.
Is there another mistake 27?
No. So that's the thing we've got to be careful of with the Venn diagrams. For some of you, it might have been easier if you didn't have this, because you might have said, well, it's those minus what they have left, and that would get me to there.
15.
So let me scooch back down a little. So we found one. Let's see if we find the other. All right. What is the probability of an event? Oh, wait. If the probability of an event happening is 6 of 11, what are the odds of the event not happening? Okay, now we got two things going on here. We're going probability to odds. That's a whole different thing. And then from happening to not. So here's how I'd kind of tackle this. If the probability of it happening is 6 out of 11, the probability of it not happening would be 5 out of 11. Now, that doesn't get me to the answer, but it gets me close. Because I remember when I'm doing probability is success over the total number of events. When I get to odds is going to be my successes over my failures. Now, this is where it gets weird. The event not happening is my success. Which means failure would be that event actually occurring. So I look at this and I'm like, okay, if it happens 6 out of 11 times, it doesn't happen 5 out of 11. Okay, so not happening is 5. So if it's unsuccessful or not happening 5 times, and there's 11 total, how many times is it going to happen?
11 minus.
Okay, so it's 5, 6, or you can write it with the colon in the middle. I just like writing odds with the colon just so I remember it's not probability that I'm working with. So that one was tricky because not only did I have to figure out the not part, then I had to convert it into odds, which is a little bit different than probability is going to be.
Can we get the ratio one? Like, was it on the other one?
It could be. Because we're dropping a pretty good hammer on this one so far, but that's good. And again, it's free reign on both reviews, so if there's
7 on that.
7 on the packet, okay, let's take a peek. Okay, now this one, the shading did show up a little bit better. Suppose 2 dice are rolled. The table and relative frequency histograms show the distribution of the absolute value of the difference in the numbers rolled. Use the graph to determine which outcome is most likely. What is the probability? Okay, so the greatest probability in the graph, both the table and the chart show me the exact same thing. So if I wasn't sure with the fractions where the greatest probability was, I can visually see that the greatest probability is right here, which would be 5/18, or a difference of 1. So like, for instance, if I roll 2 die, a 3 and a 2, I have a difference of 1. A 3 and a 4, I have a difference of 1. So that's the most likely outcome. The least likely outcome would be the shortest bar. So the least likely outcome is a difference of 5. Or you could write down the probability as well. But we can get that type of information off of a chart or a graph and not necessarily have to do a lot of math work with it. It's kind of like reading a table, sort of like some of the things that showed up in the ACT did. Just a different form of it.
For the 17, 18, and 19, when you're counting, you count the total at the bottom, right? That's what I did. That's the one across. The row,
Okay,
right?
so when we're here, right, use the chart below to answer the following questions. Okay, the probability of having a 3.0 grade point average. How many people have a 3.0?
50 people as total.
Right, 50 total people. Out of how many people were, I guess we'll say, surveyed? 106, because the total.
Oh, so that's the total.
Yes.
That's what I'm missing. What is this total? Adding those two together and not total.
Right, because this is the grand total of everybody over here in the corner. These are just totals of those individual parts. So like for instance, if we were doing 18, the probability of it being a female given, another one of those key words, given or and, given that it's a 2.0 plus GPA, okay, so here are my 2.0 GPA people, okay? That's the restriction that I'm down to now with the given part. So once I do that, out of just that grouping, how many are females? 13. So it'd just be 13 out of 30.
Oh, that is right.
Yep. And again, the order depends because you're like, well, these look real similar except now male, female, and the GPA. Right, but check out what's after the given this time.
I'm sorry, when you know, you have to look at the grand total and then you calculate.
If you don't have something that's given afterwards, you're probably going to end up using the total. Because like for instance here, given it's male, so my restrictions move. Now my restriction is here, and I'm looking for a 3.0 GPA person within that, so I'd have 22 out of 47. You always do the given part first to restrict your sample space,
Where do you get the 47?
because that's my grand total of males down here.
I didn't see that that was total, and I added the 47 to everything.
Gotcha.
Sorry, what about the
All right, let me boost down here just a little bit. All right, 22, and then we'll have another one here. The odds of a student getting an A on the test are 7 to 3. Now remember what this means. This means 7 successes and 3 failures. Now it doesn't mean they failed the test, it just means they didn't get an A. But let's think about that. If I look at that, that means there's, okay, right, like a 7 out of 10 chance that I got an A. So, if I look at it here, how many would you expect him to get an A on? Well, if he got 7 A's out of 10 tests, because that's what this told me, and he now takes 20 tests,
do they solve it?
how many A's is he going to get? So again, I probably can look at this and just say, well, it's times 2, so it's times 2, so it'd be 14. But if I didn't see that right away, I can always cross multiply and get my answer that way as well. But again, it's understanding what odds means.
When you ask us to draw it, you have to draw it.
So that's how that one would change up and work out for us.
And for the 50 spin area, what do you count with each of these 4? I think we're counting as 1, 3, 5, 8.
Yep, if you're doing experimental, you're using the chart up at top. If you're using theoretical, you're using the spinner.
But like, would you count each of these, like 4 of these inside? And then 3 of these inside?
Yeah, if you're doing theoretical, yep, you'd have to add all them up. So this guy, whoops, when you can actually see it. All right, so 23. Now we're doing 2 separate things here. Okay, we've got 50 spins total. You can't read it there, but I will rewrite it here so you can see this. So 50 spins total. Up top, this is my experimental probability. I actually spun the spinner 50 times. And just looking at a picture of it and figuring this out would be theoretical. Okay, so the probability of me getting 1, 3, 5, or 8 theoretically would be 4 out of 8 because there's 4 numbers and there's 8 spots open. So theoretically, I have a 50-50 chance of getting one of those. But experimentally, I would literally have to go in and count. I believe that is correct. 7, 5 is 8, and 8, there were 7, 11, and 15 is 26, yep. So experimentally, it'd be 26 out of 50, because that's what I literally got when I did my, and I'll just break that down. So that's barely different from what it should be. Because theoretically, and I know this isn't possible, well, it'd be 25 out of 50 instead of 26. So again, I don't think there's anything wrong with the spinner. It was just something a little bit different. But that's just being able to tell the difference between those. What else? What else? What else? 11. All right. So we're looking at ages. Okay. There are 24 students in Miss Mason's 3rd grade class, all born on different days. 11 students are boys. In the morning, the classroom is empty. One student arrives followed by another. What's the probability that when the first 2 students arrive, one is a boy and the other is a girl? Now, I have options here. So, let's see if we just try to use a little bit of logic here. Let's see what ends up here. Okay, so let's see. If 11 students are boys and there's 24 students in the class, how many girls are there? 13. Okay, that could come in handy here. So, one student arrives followed by another. What's the probability that when the first 2 students arrive, one's a boy and the other's a girl? Okay, so here's one way I could do it. I could say, now it didn't say a boy arrives first and then a girl arrives. It said one's a boy and the other's a girl. So it could be girl boy, it could be boy girl. So it's not going to matter as far as order goes. So let's see here. So let's say the boy shows up first. Okay, how many boys were there again? 11. And 24 total students. But then once the boy arrives, okay, how many girls are there? 13 out of 23. Now, some of you may say, well, wait a minute, though. Wouldn't that change if the order went the other way? What if the girls showed up first? Because then that'd be 13 out of 24. But then, oh, yeah.
But a boy left, a girl didn't leave. Why would you cut them?
Well, no, it just says, what's the problem when the first 2 right? One's a boy and one's a girl. It said nothing about the order. So, like, if we looked at it, it was going to be a boy, then a girl. Okay. Well, if it was a girl, but you start looking like, oh, 13 times 11 is still that. And yeah, that's still the same. It doesn't matter. Now, some of you may say, well, I do it with the fancy formula type thing. So how would I do that if I were going that route? I'd say, okay, well, let's see. I'd be looking at the combination of there are 13 girls, that I'm going to get 1. The combination of 11 boys, I'm going to get 1. Over the combination, there's 24 students, I want 2. And if we calculated that out, we end up with the same odds. So there is a mathematical fancy way of doing it. But again, there's nothing wrong with just saying, well, I know what the chances are of a boy and the chances are of a girl, and I'm just going to multiply them together, and that works. It works the same way. So either of those would be perfectly peachy for you to use. I can actually go back and hit that one in a second.
26 on the single sheet.
Okay. 26 on the single sheet. So let's flip back over here. All right, let's see what we got. The odds of a player making a free throw are 2 to 1. And remember what that means. That would mean made 2, missed 1, because that second number is the failure. So we're talking here in a minute about how many he makes, which means he makes 2 out of every 3 total that he does. Because if he makes 1 and makes 2 and misses 1, there's 3 total. So if he shoots 27 and he makes 2 for every 3 total, and he shoots a total of 27, how many did he make? And then just cross multiply and solve that. It is. So that's where you take something, understanding odds, and get it back into probability to help. Now, could I do it with odds? Sure. I could put, I could mess with this some, but that's going to be more work than it's worth. We don't want to make more work out of this.
Mr. Hardy, for number 27, did you look like 6, 5, 4, 3, or 27?
On one like 27, it's just you got separate situations going on here. So I've got 4 different screen sizes, 6 different hard drive sizes. Yep, in my case color, there's 3 choices. Yep, just going to be multiplying on that one.
Which one is like that where you have 4 letters and 6, 5, 4?
You may have something like if it were a license plate or a combination on a lock or something like that, where it may say, there's 10 digits available. You may not use 3 for the first one, but then you can use any letter you want for the rest. That's where you'd change that up a little bit and have some more options. Yes, sir.
10 on the single.
10 on the single. Let's flip back over. All right, we got jelly beans. So we've got 5 red, 7 green, and 4 blue. So how many total jelly beans we've got? 16.
Are we on the,
Still on the single sheeter. Number 10 on the single sheeter. What is the probability the 2 green jelly beans are chosen? Okay. So, these 16 jelly beans are in this bag. I reach in and I'm fortunate enough to pull out a green one. How many green ones were there to start with? 7, and there were 16 total jelly beans in the bag. So I'm so thrilled that I got the green one that I pop it in my mouth and eat it. So when I go to draw another one, hoping it was so good I get another green one, how many green ones are left now? 6 out of 15, because I ate the last one. And then I'm just going to multiply them across and simplify my fraction. Okay, so out of every 40 occurrences, 7 times I'll be fortunate enough to get 2 green ones in a row.
Where's that graph like on 7 or 8? Where does that go with? I don't get it.
What's that?
The thing on 7. What does this chart go with?
Actually goes to number 8.
Is number 11 just trying to fool you?
Fool me how on number 11?
It says, what is probability of rolling a 5 for a number greater than?
All right.
Bring
It will be at the end, yes. Because some of you will just figure that out right away and go, oh, wait a minute. Oh, I can just wipe this out. But otherwise, here's how I would do this. The probability might be written this way another time. Okay, probability of 5 or a number greater than 3. Well, the probability of rolling a 5 is 1 out of 6. What's my probability of getting a number greater than 3?
Yeah, then you are really high.
3 out of 6, but right. I have one repeat because a number greater than 3 is 5.
Then 3 out of 6.
3 out of 6, or 1/2.
Just left it as 3 and 16
And then just reduce it to 1/2. Yep.
that would work.
Yep, it would work.
Is number 4 wrong?
Is number 4 wrong? Let's see. A die is rolled. Find the probability of getting 1 or 5 or 6. What's the probability of getting any single? So 1/6 for 1, or is 1/6 for 5, or is 1/6 here. Do any of them overlap? No, you're never going to get, both of them at the same time.
Can't you just do it like 360 for 1/2?
Yep, you absolutely could do it just straight to 3/6. I just like showing where it comes from, so hopefully it starts to click with some of you that are getting confused.
Can you say 2 and 5?
Okay, well, one second. What's that? I'm willing to bet I know what happened here. Now, this one isn't an or, so this one isn't going to be adding, which is what I think may have happened. Because whenever I toss a coin, what's my chances of getting heads or tails? 1/2. And if I toss 4 times, yeah, be cautious, because especially if you just get done doing one like 4 where you're adding, it's real easy to add those 4 2s together and call it 8. But 2 times 2 is 4, times 2 is 8, times 2 is 16 on that one. So be careful.
How did you get number 9?
2 dice are rolled. Okay, before I continue anymore with this one, when I roll 2 different die, does what I get on the first one affect the second one at all? No. Okay, so it's kind of different than like when I was eating jelly beans and things like that.
Is 13 wrong?
So, well, let's see. So, what's the probability of both? So, chances of rolling a 5 is 1 out of 6. Then I pick it up, roll the die again, still 1 out of 6. So 1 out of every 36 rolls, I will get 2 5s.
13 wrong. So that's we're over.
Well, I didn't even guarantee that it was just on this review. It could be on the other one.
So you don't have answers on
It could be up there. All right, so let's see. 13 again, you can do visually, or you can do it trying to play with the numbers. I like doing them visually. So for instance, let me bump this up a little further. All right, so Rhonda, Jenna, Brian, and Aaron are going to a teaching conference. The principal only wants 2 of them to present on Monday. If everyone's equally likely to present, what are the possible teams? Now here's what I normally do. Okay, I see Rhonda first, so I'm just going to use R. She could get teamed up with J, B, or E. Now, is there a difference between Rhonda and Jenna or Jenna and Rhonda? Nope. They're just going to present. So when I move here, I'm like, okay, well, who could Jenna still get paired up with? Well, she's already been paired up with Rhonda. So that could be Brian or Aaron. And then I'm like, okay, are there any more here? Well, let's try Brian out. Well, Brian's already been comboed with Rhonda and Jenna, well, but he hasn't been with Aaron yet. So I notice there's 1, 2, 3, 4, 5, 6 possibilities.
Can you do it another fast way?
I don't necessarily like your chances the fast way. If you were looking for just like the number of teams there could be, you could. But with this one, especially when you're getting something like the probability of Brian and Rhonda, I'd be like, well, right there. 1 out of 6. If I'm making the tree, it's going to make this go really fast. Or then I look, okay, a team with Aaron. There's 1, there's 2, there's 3 out of 6 is a half. A team without Brian. Okay, let's see. There's 1, there's 1, there's 1. He's on the other 3. So I got the same chances of having a team with somebody as I have a team without them. But that's the thought process that we're attempting to use
What did he get for 16?
on the big one.
Yeah.
16 on the big end. Only played PlayStation 3, 31.
You can go over that.
Okay. Venn diagrams. Big packet. At Harlem, a video game poll is taken. As it turns out, 48 students say they play PlayStation 3 and another 58 say they play Xbox 360. Additionally, 17 of the students play both PS3 and Xbox 360. Draw a Venn diagram. Okay. Always start from the inside out. 17 students do both. So then, if 48 students total play PlayStation 3, how many only do PlayStation 3? 31. Because my PlayStation circle total needs to be 48. So whatever's in the middle, that's how I figure out the individual piece. So then the same thing's going with the Xbox. Yep, I have 58 total. I'd have 41 now, even though I didn't need that, because the only question I was asked is how many play only PlayStation 3. But that's, again, one of those things you have to be careful, because if you were asked how many students total play Xbox or PlayStation 3, you'd have to add all these up, and I can't just add those up.
How do you know they're not like trying to say that there's 48 that play PlayStation 3 and 58 that play Xbox, and then there's another 17?
Because if they were meaning that, what they always do on these is they'll put the word only in there. So like if they wanted this to be 46 students say they only play PlayStation 3 or something like that, they'll be very specific. Otherwise, they're just talking about the whole group as a whole. Yeah, I know. I'm like, that's not a good word to
Starting
put
for
in there.
16, you see, you say it'll come back up.
Which one?
16,
6C. Okay, now here's another one of these places we got options. It's always good to have options. Now this is one of those, I'm going to let me run all 3 of these. Because here, again, you have options, and I keep talking about being able to do it the mathematical way, yet I keep not showing it, so I better show that for one of these. So, we have a family that has 3 girls and 4 boys, so we have 7 total kiddies here. Find the probability of each if they select 2 children at random to bring to a local talent show. Okay. Now again, when you have the talent show, whether it's Anna and Michelle or Michelle and Anna, same thing. So we're going to be looking at combinations. So if I was looking at the probability of getting the 2 girls, I could either say, okay, I want a combination. There's 3 girls total. I want to pick 2. And then there's total a combination of 7 students, or 7 children, I'm sorry, pick 2. I could plug those into my calculator, which I will bring up here, which got closed in my speediness before to get out of the way. Because that's going to be easier. So I'd have 3, and again, it's math. Go all the way over to the right. Make sure you use C, not P. Would be 3, and then 7 combination 2. And the only difference when you got to C then would be, I'd have the combination of 3 pick 1, because that would cover my girl, times the combination of 4 pick 1, that would pick my boy. But the denominator still isn't going to change. If you do, like for this one, if you're doing 7, it's math, over to PRB for probability. And then if you look at the third one down, that's where the C is at.